I'm going to work on the problems from page 463 where we're finding volumes of solids revolved around the x and the y-axis, and these solids will have no holes in them. So let's take a look at number one and use that as a review of what we've learned so far. So remember, in this case, they've already given the graph to us. They've given us a decreasing line, negative x plus 1. Now this little rectangle right here confuses some students when they look at it in the textbook, so I'll explain that to you in just a second. In this first set of problems, we are revolving around the x-axis. So remember, when we revolve around the x-axis, we are in terms of x. So whatever axis you revolve around, that's what you are in terms of. So we will be in terms of x. And so as I taught you in class, you're going to put in a representative slice. And that's actually what this little rectangle is, instead of just doing like a segment like I showed you in class, showing you a radius. They are putting a rectangle in. Now, it's not necessary to show the reflection of what this thing looks like, but I will for the first one. Again, you don't have to do this reflection to be able to do the problem. But if we reflect this line over the x-axis, we'll get something that looks like this. And so that segment would go all the way across. And what we would get is a circular disc, or a circle. And so that segment is the diameter, and so we would be accumulating a series of circles. And so that's what we talked about. So we need to know the formula for the area of a circle, which is pi r squared. And this is my radius. All right, so we're going to, for number one, we're going to set up our integral. We're going to have pi. We're going to have our radius squared, and we're going to be in terms of x. We can see easily from this graph that we're going to start the accumulation at a low bound of 0 and a high bound of 1. So we're accumulating from 0 to 1, and we can see that the radius is the distance from the x-axis, coloring it again, the distance from the x-axis to the line. So that distance is negative x. I don't know why I put that in parentheses, but that's okay. The radius of the circle is negative x plus 1. So that's going to be my r, because remember, all we're doing every time is pi r squared, the area of a series of circles, and we're accumulating them. And then you're going to square that binomial. That'll give you x squared minus 2x plus 1 dx. And then you're going to do the integration, which will give you pi in the front. Don't forget the pi. X cubed over 3 minus 2x squared over 2 plus x evaluated from 0 to 1. And if you evaluate that correctly, and you should continue this out, be thankful for zeros, you should get pi over 3 for the volume of that solid. There are no units, so you don't have to write cubic or anything like that. All right, let's go into number 2, which is a very similar problem. In problem number 2, again, they've given us the graph. We're still revolving around the x-axis, so we will be in problem number 2 in terms of x. We can go ahead and set up our integral. Since we know we're in terms of x, we're going to have pi, area of a circle, r squared, and we are in terms of x. We can see from the graph that's already provided in the region, we're going to start at a low bound of 0 and a high bound of 2. And so we need to know the radius of the circle. The radius is from the axis of revolution, which is, let's change colors here. The axis of revolution is the x-axis to the curve. So that distance right there, whoops, is the radius. I'm not going to show I'm not going to revolve this and show the circular motion. We know that we're going to get circles, and this region is solid. So the length of that radius is the function 4 minus x squared. So that's going to go in place of r. I will square that binomial, and I'll probably stop doing that as well because you guys can carry forth the rest of it. So that's going to be 16 minus 8x squared plus x to the fourth dx. And then when I integrate that, I'll get 16x minus 8x cubed over 3 plus x to the 5th over 5. Don't forget the pi. There's my pi from 0 to 2. And then when you substitute and do that arithmetic, you will get 256 pi over 15. All right, next problem is number 4. Let me actually reset because I got rid of my highlights. All right, problem number 4 is another problem in terms of x. So at this point, we're just kind of following the same pattern. We know that we're in terms of x, so we can go ahead and set up our integral. We know that we are accumulating pi r squared in terms of x. The graph provided shows me that we're going to start at an x value of 0 and stop at an x value of 3. So accumulating from 0 to 3. The radius, as we have discussed, is from the axis of revolution to the curve. So it's this distance right here. And that distance is always determined by the equation of that function. So square root of 9 minus x squared. And when we square that, that's going to lift the radical, so we get 0 to 3 of 9 minus x squared dx. And then you're going to do the integration and the substitution, and you will get an answer of 18 pi if done correctly. Problem number, what's our next one? I think we're now going to be in terms of y. Yep. So now we're same deal, but now we are in terms of y. How do I know that? Because we're revolving around the y-axis. So here's the y-axis, and so now I don't have enough room to draw that reflection, but I'll kind of squish it in so it's not going to be symmetrical. So now we're revolving around the y-axis. And that slice, which is really just a segment, you don't have to worry about the rectangle, goes all the way across, and it's forming circles. But the circles are moving from low to high because we're in terms of y. That rhymes. So we are still accumulating area of lots of circles, pi r squared d, be careful, y. We're just in terms of y now. So we need to know the length of the radius in terms of y. Every radius all the time begins at the axis of revolution, which in this case is the y-axis, so the axis of revolution all the way over to the curve. Now notice we have y equal x squared, but we're supposed to be in terms of y. So we're going to have to solve this equation for get x by itself. So x is equal to plus or minus square root of y. However, we're only drawing the segment to the right-hand side right here. We're only drawing our segment, the black radius is only going to the positive side of the square root of y. In other words, the purple side is square root of y. The blue side is negative square root of y. So we're only measuring the distance from the axis of revolution to the curve, which is the purple side. So our radius is, the length of our radius is the square root of y. I'm going to substitute that there. When we simplify, that lifts the radical, and that just becomes y dy. Now for your bounds, be very careful. Your bounds go from the lowest y value right here of 0 all the way up to the highest y value of, what is our highest y value? Y x squared, oh, all the way up, sorry, up to 4, because we're going up to here. So we go from 0, a low y value, high y value. Make sure your bounds are in terms of y, not in terms of x. And then, of course, you're going to integrate that, and you get y squared over 2. evaluated from a low y value of 0 to a high y value of 4. And if you evaluate that correctly, you will get an answer of 8 pi. All right, let's go on to number 8, which is also in terms of y. Same sort of deal. We are in terms of y because we are revolving around the y-axis. That's our axis of revolution. So let's get rid of that. Whoops. Go back. All right, let's go back down. So let me get rid of that again. All right, so we're in terms of y. We're forming circles because we're revolving this around the y-axis. My radius is the distance from the axis of revolution, which is the y-axis, over to the curve. So we're going to have pi r square in terms of y. When you look at the graph provided, we're going to go from a low y value of 0 all the way up to a high y value of 4. And now I need the radius, but I need the radius in terms of y, so I'm going to take this equation and I'm going to get x by itself. So if I square both sides, I will get y squared equal to 16 minus x squared. I'm going to subtract 16 from both sides, and that's equal to negative x squared. I'm going to divide both sides by negative 1, so that gives me 16 minus y squared equal to x squared. So x is equal to plus or minus 16 minus y squared. But like I said before, the right-hand side is the positive side, so this is 16 minus y squared, which is my r value. 16 minus y squared. Then you're going to square that binomial from 0 to 4, and that'll give you 256 minus 32y squared plus y to the 4th dy. You're going to integrate that and do the evaluation, and for number 8 you should get an answer of, oh, I just see a mistake. I'm glad I caught that. I dropped my square root off of there. I was thinking, whoa, that arithmetic's not going to be fun at all. And again, you probably caught that. Good for you. I caught it. Good for me. So r is the square root. This makes it a much nicer problem. So when I square the radical, I get pi from 0 to 4, and that's going to be 16 minus y squared dy. Much better, at least from an arithmetic point of view. And then we're going to do the anti-differentiation, and we're going to do the evaluation, and if we do that correctly, we get 128 pi over 3. So that would be the volume of that region. All right, moving on to problems where they do not provide the graph. So now we're going to have to do a few graphs on our own. Let me make sure I have the right problem. Yeah, 11a and 12b are the only two that we had. Did I do number 7? I did. Right, 11a and 12b. So the only difference that's happening now is we have to draw our own graph. So in number 11, some things I want to pay attention to. Find the volume of the solid revolved around the given lines. So the first thing I want to pay attention to is that the line y equal to 0 is a horizontal line, and it is the x-axis when I graph that. And in 11a, I'm revolving around the x-axis, so I will be in terms of x. These are the things you have to pay attention to. So I have 3 boundaries that I need to graph. So boundary number 1 is the square root of x, which looks like this. So here's my square root of x. And then I have, as I said, y equal to 0 is the x-axis. So there's the boundary on the bottom in red. And then I have the horizontal line x equal to 4, which is right here. So I'm going to just say that that's 4. So the region that we are revolving is enclosed by the blue, the red, and the black. So the region we're revolving is right here. And we're going to revolve it around the x-axis. It's going to be solid because that region is totally flush to the x-axis. All right, I'm going to put in my representative radius. The radius always comes from the axis of revolution to the curve. So that purple segment represents my radius. I'm supposed to be in terms of x, so the radius distance is top minus bottom. So the top is the square root of x minus 0, which is the square root of x. So accumulating circles, pi r squared in terms of x. When I look at my graph, I can see that the lower bound is 0 and the upper bound is 4. The radius is the square root of x. When I square that, I will get x from 0 to 4, and the arithmetic and the integration will be quite simple on this one. And if you do it correctly for 11a, what is the answer? So you don't have to look it up. Sorry, I went too far. 11a, you should get 8 pi as your answer. Moving on to 12b, which is the last problem. We have to make our own graph again. And again, in 12b, we are revolving around the x-axis. Is that the one that I actually picked? 12b, let me make sure. Yeah, 11a, 12b. All right, so we're revolving around the x-axis again. So we will be in terms of x. So my graph for 12b, I have 2x squared. So 2x squared is a parabola that opens upward like that. And then I have y equal to 0, which is the x-axis again. I have x equal to 2, which is a vertical line right here, 1, 2. So be careful about the region that we're talking about. So if you look at the blue and the red and the black, the region that we are finding the volume of is this orange region right here. We're ignoring anything on the left-hand side, and we're revolving that around the x-axis. So if we revolve around the x-axis, we are in terms of x. So we're going to need a radius, which is always from the axis of revolution, so right here, to the curve, which is right here. And to find the length of that segment, I'm going to take the top of the segment minus the bottom of the segment. So that would be the blue curve, which is 2x squared, minus the bottom, which is 0. I don't really need that, so the length of the radius is 2x squared. Now I'm going to set up my integral. I'm accumulating area of circles, so pi r squared in terms of x. The low bound is an x value of 0. The high bound is an x value of 2. And the radius is 2x squared. So when I square that, I get 0 to pi of 4x to the 4th. And then I'm going to integrate that, or you're going to integrate that and evaluate that. And when you do for 12b, you should get 128 pi over 5. And so that's your first set of problems on finding volumes of solids.